Okay, then how to learn the parameters WAA, WAX, WAY, and BA and BY. Same, backpropagation and SGD. Using training data, we can compute the gradient using backpropagation, and because it is very difficult to compute the full gradient at each time, we compose a mini batch from some random sampling or random shuffling, and then using the only mini batch we compute the gradient using backpropagation and update the parameters using gradient descent rule. With some step size, you can update the parameters. Okay, everything is the same. Backpropagation and SGD is the key to update the parameters. But backpropagation is not so simple. So how can we calculate the backpropagation step using the recurrent neural network RNN with various lengths of input and various lengths of output, so various ranks of your architecture. So to understand the backpropagation, we have to draw the computational graph. So we have to draw graph that explain the computational process, the inference process from the input to output. So basically we have a parameter W, A, Y, P, Y for generating Y hat value. And we also have parameter WAA and WAX, BA to generate the hidden state vector A. At the beginning, we start from some predefined initial hidden state A0, and the A0 and the parameter WAA, WAX, BA, and X1, the first input, go to some linear function, right? So this is just linear operation. WAA times A0 plus WAX times X1 plus BA, and which goes through some nonlinear activation function G, and which make the A1 hidden state, the new updated hidden state, and this value go to here to compute the output Y hat. For this process, we use the parameter WAY and BY, so which make the some linear operation here, and then we compute the Y hat one. Okay, this is easy for the first step. The second step also very easy, using X2 and the parameter WAA, WAX, BA, and the hidden state A1. You compute again some linear combination, and then compute the nonlinear activation function to compute A2, the second hidden state, and this one and the parameter WAY, BY, you compute some linear combination and nonlinear activation function to compute Y2 hat. For X3 as well, use the same parameter And this hidden state to compute A3, and this one go here, use the same output parameters to compute Y has 3. Okay, so you can define this way up to the, let's say, the end time x capital T. And go to A capital T. This one, again, use the same parameter again to find Y capital T hat. Right. So there are a lot of paths from the parameter WAA, WAXPA to the output Y1 hat, Y2 hat, Y3 hat, up to Y hat T. There are many passes, right? A lot of passes from the parameters and the output Y. Essentially from Y hat 1, Y hat 2, Y hat 3, up to Y hat T, and the reference label output Y1, Y2, up to Y capital T. You can compute the loss value. Okay, you can define loss value, which define the distance between the estimated Y hat and the true label Y. And from the derivation with respect to Y hat T of your loss function, you will update the WAA, WAXPA, and WAYPY as well. Okay, the backpropagation here, the B is backward propagation. So backward pass means or the reverse pass from the output to your target parameters. So since there are a lot of forward paths, there are a lot of backward paths as well. Okay, there are a lot of backward paths. Okay, so you consider every path from output to your parameters in this computation graph and compute the partial derivative for each path and then just linearly combine the partial derivatives. That is backpropagation process. Okay, it looks very complicated, but fortunately we have a very nice closed form equation which basically consists of sum of some matrix multiplications. Okay, so please watch the Stanford lecture videos where you can find the exact form of backpropagation. Okay, but here I want to highlight the correlation between x1 and y hat capital T. To model or to learn the correlation between x1 and y hat T, we have to take the path from x1 through x at T. We have to consider this path to understand the correlation between x1 and y at T. So the backpropagation value obtained from this path, this backward path, will give you some information or will store some information to your training parameter WAA, WAXPA. Okay, this is very important, right? And also this path will give you the correlation between x1 and y hat t to the parameter WAY and BY. Okay, but when you look at these green passes, you have to go through many hidden states. You have to go through many A1, A2, A3 up to A capital T. And at each time, you have to multiply the same matrix WAA, WAX at each point. Okay? So which introduce some identity plus weight matrix times identity plus the same weight matrix and so on. So which is identity plus same weight matrix power capital T part in your backpropagation process. So the correlation between x and y hat t naturally computed from identity plus some current weight matrix power to capital T times something. Okay? So the important thing is we have this part. And this part and this term will increase as the distance between x1 and y hat t grows. Okay? And why this is very, very important? Since W matrix is the same, and if W is not zero matrix, the norm of I plus W either grow to infinity very fast or decrease to zero very fast. It has very huge exploding gradient issue or vanishing gradient issue, whatever this part you have. Okay, so this is the main difficulty when you train recurrent neural network. Recurrent neural network usually have some very difficult issue, especially when you want to train something on the correlation between very beginning input and the very last part of your output. Okay, so we have to solve this. We have to solve this, right? We have to solve this vanishing and exploding gradient issue. So let's go back to just normal fully convoluted neural network or convolutional neural network. In that case, we also have vanishing gradient and exploding gradient issue. So when we have very deep structure, usually it is very difficult to train the very deep structure model. So you maybe observe some very bad training error. Although you increase the number of parameters, your training process go to very bad point, and so training error also very bad. So to solve this issue in convolutional neural net architecture, some people use residual structure. Okay, such shortcut give you very nice backpropagation property. So we can have very nice training property. So we can stack 100 layers to have very nice performance. Okay, so maybe we can bring this idea, the shortcut idea, to recurrent neural network. Then maybe we can be happy with the training process. But the problem is here we use different parameter for each layer. We use different parameters. Okay? This is the main difference things. So although you put the residual part, when you use the same parameter again and again, we still have some vanishing and vanishing gradient issue. What I mean is, if you have different parameter, is the backpropagation step make this product identity plus W1 identity plus W2 times identity plus W if the last layer is capital L, this one. And if, let's assume W1, W2 up to WL are ideal in the matrix, then roughly the norm of this one still close to 1 because the sum of direction multiply, sum of direction shrink, sum of direction amplify, sum of direction shrink, and so on. And all the amplification and shrink totally random. So in the end, you expect almost identity matrix, which means you can train almost every layer without vanishing or exploding gradient issue. But when you use the same parameters, this is just simply I plus W multiply with the same matrix again. So I plus W part to L, right? So this make your residual process still have vanishing gradient or exploding gradient issue, even with the shortcut process, right? So recurrent neural network, which has the same parameter all the time, which can save the number of parameters, which is great, but because of this property, we cannot train the neural network very well. Okay, sorry. So here I used the shortcut thing, which actually is this one, right? So more bad. Okay, without shortcut, the backpropagation is just W part to capital T, which is very bad, right? And even with shortcut, we have I plus W part L, which cannot solve the vanishing or exploding gradient issue.